The universe is a wide and complex place with billions of planets and stars, as well as countless theories and unanswered questions. Scientists may know most of what is going on in space. One of the few things that, until this day, scientists cannot explain are black holes. For years, black holes have been a mystery to the people who have studied them. From the great minds of Albert Einstein to Stephen Hawking, there have been several studies to try and understand these unknown cosmic entities. It all goes back to the late 1700s, where scientists thought about what would happen if an object had gravitational pull so great that not even light could escape it. 2 centuries and countless of theories later, have we finally deciphered it? Hello there, and welcome back to the Discover Space channel, where we explore the cosmos, the good, the bad, and all in between. Be sure to subscribe if you haven't already, and let's get on to the video. Within the first 100 millions of years of the universe, things were significantly different. Gas clouds and dark matter were just beginning to gather together because of gravity. And the very first stars, which were merely abundant in helium and hydrogen, started to develop. But astonishingly, some massive black holes with masses up to 1 billion solar masses had already developed. If we take into account the conventional model of black hole development and production, the incredibly young universe, which is less than 1 billion years old, could not have existed for long enough to cause the black holes to swell up to 1 billion solar masses in the conventional manner. Furthermore, quasars in particular, which are extremely huge black holes, shouldn't have formed at the period of the universe's history if our present black hole models are correct. They did, however, indeed emerge in the early universe. So, how did these enormous black holes develop in the young universe? And does this alter the way we understand how black holes form? Let me start by giving you a short overview of a quasar. The acronym quasar stands for quasi-stellar radio source. A supermassive black hole that is actively devouring gas at the heart of a far-off galaxy is known as an active galactic nucleus. One of the universe's brightest lights and most formidable objects are quasars. Some quasars can be thousands of times more luminescent than our galaxy. The intriguing question is, though, what gives these things their incredible power? Their environment could be an explanation to this. Typically, quasars are found in galaxies with abundant gas reserves. The gas whirls around the black hole whilst plunging into it in such dense atmosphere, heating up as a result. The whole electromagnetic spectrum is therefore covered by the radiation it produces. Quasars are often seen in distant galaxies because the supermassive black holes in neighboring galaxies do not contain as much gas. Even Markarian 231 is nearly 600 million light-years away from us. Then, how do these stunning spinning structures come to be? 2 important hypotheses exist now that explain how black holes normally arise. According to the first and most well-known theory, a large star's death can result in the creation of a black hole, with a mass of up to about 100 times that of the Sun. The material around this black hole may eventually be absorbed by it. The result is that the black hole continues to enlarge until it attains supermassive status and is much more enormous than that of the Sun. However, according to experts, no black hole can ingest enough matter in under 500 million years to grow to be as massive as 1 billion suns. This is due to the fact that matter settles into an accretion disk when it starts to assemble around a black hole. At speeds close to the speed of light, the material in this disk orbits the black hole. The disk heats up as a result of the motion and ejects radiation jets with a wide range of wavelengths. This radiation's tremendous pressure displaces neighboring matter, slowing the black hole's rate of mass consumption. The Eddington mass limit refers to this hypothetical maximum rate at which a black hole can accrete matter. A black hole is anticipated to generate strong winds even if it can accrete matter more quickly than the allowed rate. The growth will be stopped because these winds will further push the surrounding stuff away. All of these characteristics restrict the rate of a black hole's growth. Consequently, if the scenario is true, it conflicts with the idea that quasars evolved in the earliest years of the universe normally. This would get us to the second quasar theory that might be true. It states that some short-lived stars, which may have had a lifetime of around 250,000 years, imploded to create black holes that are significantly more massive than our Sun, around 100,000 times. In this instance, the seedling black hole had the potential to quickly accrete mass corresponding to billions of solar masses because it was quite big. This notion is further supported by the estimations that quasars must have had between 10,000 and 100,000 solar masses at birth. However, the parent star must be extraordinarily massive, nearly tens of thousands of times more enormous than the Sun, for such a black hole to form. But in the known cosmos, we have never seen stars that size. Even the largest star so far identified only has a mass of around 300 times that of the Sun. Additionally, we are unaware of any present mechanisms that could promote the development of stars with masses of thousands of times greater than the Sun. But then again, we are aware that the early cosmos did not exist under the same circumstances as it does now. So these stars might have originated in the early cosmos in accordance with calculations. It is plausible that huge stars originated at the intersections of strong streams of turbulent, dense cold gas, albeit the occurrence would have been extremely rare. But for stars to develop, this would have needed some incredibly unusual circumstances, such background of strong ultraviolet light or supersonic fluxes between gas and dark matter. And sadly, none of these unusual circumstances are comparable to the surroundings where these early quasars have been discovered. What then is the quasar formation's explanation? Scientists use simulations of the gas streams to find an answer to this query. A dense cluster of elements in a cold cloud typically falls under gravity to become a newborn star. However, there is too much turbulence present to allow for such a collapse. Therefore, in the simulations, the turbulence caused by the colliding streams stopped the development of typical stars, such as the ones we see today. Instead, this caused the cloud to become so huge in the simulation that it suddenly collapsed into massive stars that were nearly 30,000 to 40,000 times the Sun's mass. A supermassive black hole with billions of times the mass of the Sun can arise and grow in just a few 100 million years if the gas from the streams keeps feeding the clouds. It illustrates how supermassive black holes might have developed in the absence of unusual circumstances at the intersections of gas streams. So, what do you think? Do you think with these theories and hypotheses that we have, is the black hole's origin finally deciphered? You let us know in the comments section below. And also, you can include other cosmic adventures, possibilities, theories, hypotheses that you want to explore next. And we shall see you then.